Thank you. Yes, I think most of the work actually went into inventing this title. Good afternoon. My name is Jochen. I'm from the University of Mannheim, and this is joint work with my supervisor, Frederik Armknecht. And we're going to have to talk about a lot here because there's a lot going on in this paper. But the general context is very similar to what we heard in the first talk. So assume you have two databases, in this case A and B, Alice and Bob, and they want to compute basically an inner join. So they want to find out, okay, which individuals are present in both databases. But now assume that this is also like a sensitive database, so basically a prison record or medical records, whatever. So you cannot do this on the plain text personal identifiers because the presence of an individual in a prison record is already very sensitive information, for example. But you can also not use hash functions to hide the plain text identifiers because they are error prone. There might be spelling mistakes, there might be different spellings, whatever. So instead, what is being done is to apply a similarity preserving encoding to these plain text identifiers. And there are also like another way to approach this is multi-party computation, but as we also already heard, this is very slow. And just to give you a context, this is actually being used in practice. For example, in Brazil, they have a cohort study with over 100 million participants. So this is the scale of this we're dealing with. So the attacker model in that is that we actually have this linkage unit here, which is the one who performs the matching based on the similarity preserving encoding. And we have to assume that this linkage unit is honest but curious, meaning that it has, of course, given the access to the encoded database, but also to a plain text database that has some overlap with the encoded database. Think of it as, for example, the phone book, where you also have in some countries the names and addresses of people in there. They might also appear in let's say, the patient registry of the local hospital. So the attacker tries to de-identify individuals from this encoded database. And how is this done? Well, the standard attack for that is the graph matching attack. I'm not going into too much detail as to how that works. We can discuss that in the poster session. But the general idea is because these encodings are similarity preserving, you can kind of treat the similarity between two records as a graph, and you can compute a graph on the plain text data and on the encoded data, and because the similarities are almost the same, the graph structure will be the same, and then you can reduce this to a graph isomorphism problem, and you end up with a linkage from the encoded data to the plain text data, and you have broken the encoding. The reason why this works is that a lot of the standard encoding schemes that we saw are perfectly similarity preserving. So you see there is almost perfect correlation between the similarities in the plain text and the encoded data. And in the early days of PRL, that was actually a desired property. So people developed schemes that achieved exactly this. After the DTMAs, the graph matching attacks, emerged, people started noticing that this is not good. So instead, they started doing something like you see here in the upper left which is that if two records are dissimilar, you basically get a similarity score of 0.5 cumulatively. So you don't get any information, more or less like a binary information. If your records are similar, or the similarity is 0.5, which tells you nothing if it's below a certain threshold. And this prevents the graph matching attacks, and the community was very happy. And I thought, okay, is this actually secure? The standard scheme that achieves these properties is Bloom filters with added diffusion, or BADs, which is a scheme that was presented 2 years ago at PETS, PETS 2024. And it basically works by first computing Bloom filters. I will show that in animation in a second. And you compute or you hash the bigrams of the string that you want to represent into Bloom filters. So you have every bigram, and every bigram corresponds basically to a bit vector, which is the Hamming weight of the number of hash functions that you use to populate the Bloom filter. And then you do a bitwise OR operation of all of these individual, like intermediate representations, and then you end up with a Bloom filter, and that represents your record. But the Bloom filter is like perfectly similarity preserving. So instead, what you do next is you have this diffusion layer where you have a diffusion size, and each bit of this Bloom filter with diffusion is the XOR of, in this case, 3 bits of this Bloom filter that you calculated before. Right? So you go through and through and through, and in the end, you have a Bloom filter with diffusion that hides all the similarity of the similar records. Okay, so that's good because it hides the similarity of the similar records. So graph matching attacks are not possible. But what can we say about the security of the encoding itself? So one thing that immediately struck my attention was that this diffusion layer here is entirely linear. It's an axial operation. What is nonlinear is the creation of the Bloom filter. So there might be some hope that this thing in total is secure, but is it really nonlinear? Because with the parameter settings that are usually being used in encoding, these intermediate Bloom filters are actually really sparse. So they are typically of length 1024. A typical record that we were dealing with has around 20 to 30 diagrams. So most of these bits in the intermediate Bloom filters are actually going to be zero, or in the bigram representations. And if a lot of these bits are zero, and you OR them, well, there's no real difference between ORing them or XORing them. I mean, the only case when XOR, the result of an XOR and an OR operation differs is when both bits of ORing and XORing are 1. And because this is incredibly rare, you can see the probability of a bit being 1, being 0 here in the top right, because it is incredibly rare, this entire thing is basically linear. And we have approximate additive homomorphism, which means if we export two Bloom filters with diffusion, what we get is approximately a Bloom filter or an encoding that represents the XOR of the plaintext. And this in itself is also already pretty bad, but there's also a second property, which is that Bloom filters with added diffusion leak more or less the size, plaintext size into the encoding, which also makes sense because if the input is sparse, if it's short, then a lot of these intermediate bits would be 0. If the XOR is zeros, you end up with a lot of zeros in the AD. So we also have like a leak of the plaintext length into the encoding. And you can combine these two properties to craft a attack. And we call this the homomorphism-based graph matching attack, because what it basically does is it searches for combinations of encodings, of PAD encodings, that more or less result in the 0 vector, and then does the same with the plaintext, and then matches that. And we end up with a slightly different form of the graph matching attack that we saw in the beginning. So these things are unfortunately very insecure. This is the experiment that we ran on a synthetic data set, which means it is a data set that was specifically crafted to include this kind of structures that the attacker is able to find. But I mean, it's not quite realistic, but I would argue that the security of an encoding scheme should not depend on the data you're encoding. And you can think of situations actually where this situation like this might happen. So now that has been broken, what do we actually do? Well, we call SAUL. And SAUL is the scheme for anonymous utility preserving linkage, another acronym that I spent way too much time on coming up with. And the idea that I had here was that the general design of the Bloom filters with diffusion has merit. It is very good at preventing these standard graph matching attacks. So all we have to do is avoid this homomorphism and avoid the correlation of the Hamming weight of the Bloom filters, of the encoding with the length of the plaintext. And the way we do this is we replace the OR operation in the creation of these intermediate Bloom filters with a majority function. And there is a whole lot of arguments why the majority function is actually a good choice for that. Again, I would refer to that or defer that to the poster session, but just take it as a given for now. So again, we have these intermediate bit representations of the individual bigams. And instead of ORing them for the final representation, we compute the majority of it. So we have a single bit vector in the end, where each bit is the most common bit in all the representations of the individual bigams. If we do this, then we have again something that has like a perfect correlation between the plaintext and encoded similarities. So this is not secure against the standard graph matching attacks. So we do this diffusion trick again. Basically, repeat this process a couple of times and just export the resulting majority bit vectors. And this gives us again a scheme where like only similar records are similar plaintext records have high similarity in the encoded data. Okay, so what about the security of SAUL? Well, here on the left, see the correlation between the Hamming weight of the encoding and the length of the plaintext. So there is none, which is good. We learn nothing about the length of the plain text. In the middle, you see the similarity correlation, which is very similar to what we saw on the blue filters with added diffusion, which is good. So we shouldn't see so we shouldn't be able to compare graph mixing attacks. On the right, you can see the probability that a diagram includes a certain pattern, which is a security property for a different kind of attack, but then it's also like close to 0.5, so you don't have any additional information. What about the utility? Well, it achieves high linkage quality, so it's very good at actually finding like a person that belong together. It's also quite fast. You can see it scales linearly, and it takes about 14 seconds to encode 100,000 records. It's about 2 seconds slower than the blue filters with added diffusion, so the performance penalties are marginal. And that was a lot of content for 10 minutes. And if you have questions, there's my poster. He will be there after the session. Thank you.